that causes a huge difference in what is actually gonna happen.
Is it because the Earth's traveling in a circular path and the rocket's traveling in a straight?
Okay, you think Earth's traveling, going around the sun?
Doing it, so.
Yeah, if you're traveling at 0.9 times the speed of light for a year, you can assume that the orbiting of the Earth around the sun is not significant.
Yeah, if you're almost a light year away.
Or half a light year, I guess, there and back.
That's true, yeah.
I don't know, there are no planets within a half light year of Earth, are there? Other than this mysterious planet X that doesn't much of. I was thinking Alpha Centauri was like 2 point something light years away.
Yeah. That's the closest.
How far is the
star,
moon
I think,
away?
Yeah.
How far is what?
The moon.
240 something thousand miles, I think.
Sure. I look it up every time. I guess people do.
Less than half a light year, that's for sure.
Yes. All right, so think about this one. You're in the rocket. So picture we're all in the rocket. This is our spaceship right here. We're going out. What happens in a half year?
We reach the plane.
And then what do?
Turn around and come back.
What does it mean to turn around?
Go back the way that we came.
Okay.
1.25 light years.
Say it again?
1.25 light years.
What?
This is the moon.
No.
No.
Or light seconds, I'm sorry.
Okay. Yeah, definitely.
Light seconds, so.
Yeah.
That's a huge difference there.
Only by a factor of, what, 30 billion?
Yeah, that's something. Few million.
Yeah, that's a fraction of a light year.
All right, let's do it from this point of view. I'm gonna head toward the door and then I'm gonna turn around. So I'm heading towards the door, traveling 0.9 times the speed of light. I get there, I turn around. Now from my point of view, the door came at me and then went away. Think about it in terms of what was involved in my turning around from your point of view, or from the door's point of view, turning around.
You had to stop yourself and then reapply the same force to go back at the same speed.
And the door?
Door didn't do anything.
The door didn't change.
That is the huge difference between these two situations. The rocket ship has to accelerate in order to turn around. Accelerate in the physics term of meaning velocity has to change. The Earth doesn't. The Earth just basically sitting there from the rocket's point of view we're not, again, ignoring the orbiting around the sun. So the Earth basically sits there. So there's a huge difference in the fact that this drops out of the reference frame, or the Earth drops out of that reference frame and then back in. So the fact that forces have to be applied, external forces have to be applied to the rocket, collapse this scenario right here.
What if the mass of planet X was so big that it could like orbit around planet X once and then shoot back?
Gravitational slingshot, you mean?
Right. But the mass of planet X would have to be huge because you're traveling at 0.9 the speed of light.
Then probably bring general relativity effects into it, and let's see, so I think that would cause even greater difference in the time. So on Earth, they would age more than 2 point whatever years.
Okay.
All right. So that's the twin paradox. Now, all of this is all nice and word examples, we can do calculations. However, where's the experimental evidence? So in 1905, Einstein comes out with his paper on special relativity, this stuff. 1905, he also comes out with his paper on the photoelectric effect. 1905, he also comes out with a paper on the basis of general relativity. 10 years later, he comes out with the second paper on general relativity with the math. And then the first evidence of general relativity being true happens, I think 4 years after that, 1919, somewhere in there. Special relativity didn't get its first concrete evidence until 1941. The Rossi Hogs Hall experiment. There are these particles called muons. Generally symbolized by a mu, just like an electron symbolized by the letter E with a negative sign. Muons are symbolized by mu with a plus sign if it's a positive muon, negative sign if it's a negative muon. Oh, there we go. Now muons are basically coming from the sun, and as they come towards us, they break down. So they tend to decay into a positron plus a anti-electron neutrino plus a muon neutrino. These are just really tiny particles, generally referred to as WIMPs, weakly interacting mass particles. So they have mass, but it's really hard to detect them. But muons basically decay into electrons. The mass of a muon is roughly 207 times the mass of an electron. So very distinct particles. As if I have, at that point that you were using a cloud chamber, bubble chambers wouldn't exist for another 15 years or so. Basically, a cloud chamber is you have I was about to do the superheated liquid, that's the bubble chamber. You have basically, in a sense, a mist here that when the charged particle comes through it, it's going to interact with the stuff in the mist, and you'll see a trail. And so as it comes through, you'll see it sort of traveling like that, and you'll see these little wisps. And it's possible to make one. The former high school chemistry teacher across the hall actually made a cloud chamber.
Isn't that where you can detect the, I forget, it's like not gamma, but like beta radiation or something like that? It's like you need a sponge and a cup and a black piece of paper and some sort of chemical, I forget.
Yeah, pretty much.
Yeah, okay.
That's it. The black just for the background.
Yeah.
All right, so you can detect, and then if you expose this to a magnetic field, you can get the particles to bend as the charged particles come in. And if you see a mist and you see the bend, you can then go, oh, that bent like this, and therefore that's a lighter particle, that's an electron. That one didn't bend as much. Oh, that's a muon. That's the basic type. Looking at it. So we can actually count the number of muons. You set up the chamber, and then you just start. At that point, probably, you might be filming it, but you probably have some grad student grunt in there with a piece of paper and a pencil counting. And so they went to the top of this mountain, and they counted the number of muons. They went to the bottom of the mountain, and they counted the number of muons. And so then they did a comparison of the number here and the number here. And I did not write down the distance. Because my more complete notes are sitting at home, so, oh, actually, I'm probably faster than this thing. Rossi Hall, you just bring up the Wikipedia page on that. I'll hold up. So, beta for the muons, 0.994.
What are you looking for?
The height, the distance. Let's say it's 100 meters. Really good scan.
Type in Rossi Hall and Wikipedia pulls up Rosie O'Donnell.
Mount Washington,
Yeah, okay, what's the height?
1,916 meters.
1,916 meters. That's Mount Washington in what, New Hampshire, someplace like that?
Yes.
Okay. All right, So they basically counted up here, and then they went down, apparently closer to sea level. They might have done the second part in Boston itself. But they counted the number of muons at that height, counted the number of muons at this height. Right, and you can put that away this way.
Yeah. I was saying.
The average lifespan of a muon is 2.19691 times 10 to the negative 6 seconds, or we'll just round that to 2.197 microseconds. That is how long that these things will survive before they decay. So you would do two calculations. You do one calculation, you assume that these particles that don't, you assume the special relativity is not true. Galilean relativity is true. So if it's going to be traveling 1,916 meters, and it's traveling at 0.994 times the speed of light, so the speed is 0.994 times 3 times 10 to the 8 meters per second. Question is, how much time takes place from the time that the particles are there to the particles get down there? How long does it take for the particles to travel that 1916 meters? I guess first speed, what's the?
298.2 times 10 to the 6
meters per second. And so that should be the distance divided by the time. So 1916 divided by that number you just said.
Is 6.425 times 10 to the negative 6 seconds.
Now, if we divide by the average lifespan of it, so we basically have 6.425 microseconds divided by 2.197 microseconds. It's somewhere around 3.
Yeah.
Is 2.924.
All right.
Yeah.
So that's a bunch of average lifetimes, almost 3 average lifetimes for these muons to get from here to here. Not many are going to survive it. So if we start out with 1,000 particles here, then we would expect, somewhere around 40 or so there. The numbers are shooting off of memory here, but the gist is solid. So that assumes that there is no special relativity. The time is the same for us as it is for them. Now, let's take into account the differences here. If beta is 0.994, I know gamma is 9.142. That you guys figured that out earlier. So time on Earth is equal to gamma times the proper time. In other words, from the muon frame of reference. So the amount of time it took them to get from one place to the other, that is from the Earth's point of view. So we have 6.425 microseconds is equal to gamma 9.192 times the proper time.
142? That's what I thought it was.
Oh, 42.
$7.028 times 10 to the negative 7.
Alright, so 0.728 microseconds? Wait, you said
0.028, so 7.02, or, excuse me, 0.7028 microseconds, yeah.
So if special relativity is true, there should be a factor of almost a little bit more than 9 between their time and our time. So we look at this thing, we measure it going this fast, heading down here, and we say almost 6.5 microseconds passes, but from their point of view, 0.7 microseconds passes. Well, if this is their lifetime, most of them are still around. What I would expect to see is almost all of them still surviving by the time they get down here. And in fact, that's what they found. Almost all of them survived. Because from their point of view, from the Muon's point of view, they do not age as fast as we do. And this was the first major piece of evidence that special relativity was true. So, let's think back to the two different points of view. From Earth's point of view, we've got this almost 2,000 meter difference, and 6.425 seconds passes, or microseconds passes. From their point of view, 0.7028 microseconds passes, and they see the Earth coming up towards them. They don't see themselves as falling, they see the Earth as coming towards them. From the Muon's point of view, how far did they travel? Oh, strike that. From the Muon's point of view, how far did the Earth travel? Because again, the Earth's coming towards them. They both agree, the Muons and the Earthlings both agree on the speed. They just disagree about what's moving. Earthlings say the Muons are moving, Muons are saying the Earth is moving. Because Muons have sentience in this example, apparently. So if 0.7028 times 10 to the negative 6 seconds passes from the Muon's point of view, and the Earth is traveling at 2.982 times 10 to the 8th meters per second, how far did the Earth travel?
The 2.982.
2.982, I pulled that from here, I just put it back in scientific notation out of engineering notation.
Is 209.6.
209?
Yes, 209.6.
So we have two different viewpoints here. From Earth's point of view, Muon is traveling at 0.994 times the speed of light, and it travels for 6.425 microseconds. From the Muon's point of view, the Earth is traveling up towards it at 0.994 times the speed of light, and it does it for 0.7, wherever it is, about 0.7 microseconds. Earth people say that the thing traveled almost 2,000 meters. The Muons are saying that the Earth traveled it at basically 210 meters. Not only is the time different, but the length is different. And this is known as length contraction. So we have time dilation, and generally called length contraction. So let's go back to the Earth rocket ship problem. Earth, rocket, planet X. As the rocket goes to planet X and back, or as planet X comes towards the rocket and back, how far the rocket people say that the planet X traveled and how far the people on Earth say the rocket traveled, they'll have two different distances. Which is the proper frame? Remember, proper is you're doing the measurement when it is at rest relative to UR.
There isn't one?
No, there's a proper frame. In my simplified scenario here. Again, we're ignoring any orbiting around around stars or anything like that.
Then it would be the Earth.
Yeah. Because from the distance from Earth to X is a constant. From the Earth's point of view, X does not move at all. So that's the proper distance. So when you're doing the length contraction, it's not like it suddenly flips and that this proper time and this proper length don't go to the same reference point. From our Earth rocket point of view, proper time is on the rocket, proper length is from the Earth's point of view. But in essence, they mean the same thing. So I usually find it helpful when doing these problems, you find gamma, and then you figure out, all right, so which one's gonna be longer? And just multiply or divide so that that one that's supposed to be longer is longer. And so I'm gonna leave you with this question, which we'll answer on Monday. How fast does an 11-foot car need to travel in order to fit into a 10-foot long barn or garage? To fit completely, how fast does an 11-foot car need to go to completely fit inside a 10-foot garage?
Fast enough that when it hits the wall, it compresses by a foot.
Assuming no compression, it fits completely inside without hitting the other wall.
It's not, you'll go through. Just kidding.
Special relativity tells you that you are correct and wrong at the same time. So
It's nice to hear.
we will, so we'll do it the simplified version on Monday, and I doubt if we'll get into it on Monday, but potentially get into the more sophisticated look at it from both points of view. But that requires defining simultaneity and more stuff that you always thought was true that actually is not.
That sounds like Schrodinger's parrot, or Schrodinger's cat.
Someone once described education as they first teach you what, then they teach you what and how, then they teach you what, how, and why, and then they realize they have nothing else to teach you, so they teach you to question everything you've ever learned. So I'm teaching you to question everything you've ever learned.
See you on Monday.